Hello dear students, this lecture is in continuation with the previous lecture on data compression. In this we will learn some more techniques for direct ECG data compression techniques, and one algorithm in that is CORTES algorithm. The basic advantage of turning point, that is TP approach, what we have discussed in last lecture, is that it preserves the important attributes of the QRS complexes. But the main disadvantage in that was that data compression is independent of the morphology, whether it is the fast QRS moving complex or the relatively slow moving T and P waves or the isoelectric region. On the other hand, we have discussed about AZTEC, which has a much better data reduction capability and adapts its coding more to the nature of the signal region as well as eliminates baseline drift. However, even after smoothing, the reconstructed ECG waveform from AZTEC data may not be clinically acceptable. Occasional complete loss of the P wave, loss of PR and ST segment durations, a widening of QRS complex, and a decrease in its amplitude are some of the problems associated with such waveforms. Thus, to overcome the limitations of both the TP and AZTEC approach and keeping into account the advantage of these, another algorithm was proposed, that is coordinate reduction time encoding system CORTES algorithm. So let's see the flow chart of CORTES data compression. So first is we have to apply the TP algorithm to the fast changing morphologies of the ECG waveform, and then we have to apply the AZTEC algorithm to the isoelectric region of the ECG waveforms. So this figure shows the flow chart. It executes the TP and AZTEC algorithm in parallel on the incoming ECG signal, and it is based on the experimental determination of line length threshold, and it decides whether the AZEC data or the TP data is to be retained. Whenever an AZEC line length exceeds the length threshold, then CORTES save the AZEC line, otherwise it will save the turning point data points. So TP is used to encode the QRS complexes. Only AZEC plateaus are generated and no slopes are produced in that. Now let's move on to the detailed description of this algorithm. As the ECG signal is sampled, CORTES simultaneously applies AZTEC to the isoelectric region of the ECG waveform and the TP algorithm to the higher frequency region of the ECG signal. The algorithm uses a line length threshold which is obtained by experimentation on the database. Once an AZTEC plateau is produced, the program CORTES saves the AZTEC data only if the plateau is longer than line threshold, or it saves the TP data only if the plateau is shorter than or at most equal to the line threshold. So in this case, only AZTEC plateaus are generated and no slopes are produced. So to preserve the slope of the QRS complex, the CORTES algorithm uses turning point instead of that AZTEC to encode the high frequencies that are attributed to it. To fasten the process of coding, the TP data are stored directly into the array. So these are the arrays it shows. So we have two array pointers P1 and P2 So by using these two array pointers, CORTES determine the difference between so-called probationary, why we are calling it as probationary, because we have to take the decision whether it belongs to TP or AZTEC data and the permanent data. So a marker is required to identify the transition between the TP and AZTEC data, and the marker can be any binary value other than an A to D converter output value. If an 8-bit A to D converter is used, then one quantization level is to be set apart for marking the reducing the amplitude resolution from 256 to 255 levels. So how we can convert that probationary data to the permanent data? The first array location of the CORTES algorithm is made equal to the marker P1. It is set to 1 and P2 is set to position 2. So successive points are stored as probationary TP data while advancing pointer P2 until an AZTEC plateau is found. Now if the duration of the plateau exceeds the line threshold, an AZTEC plateau is stored, as you can see in figure A, and both the pointers P1 and P2 are moved. On the other hand, if the duration is less than the line threshold, then TP data are made permanent. So after the data are stored permanently, the CORTES algorithm starts the process of producing another plateau while simultaneously storing TP data on a probationary basis. Reconstruction of the original signal from the encoded data of CORTES is done by expanding the AZTEC plateaus and interpolating between each pair of the TP data points. After this, parabolic smoothing is applied to the AZTEC portion of the reconstructed ECG waveform to reduce the discontinuities. So we can see the example of pointer and data transition in the CORTES algorithm. So figure A, that is our last permanent data AZTEC, and new also in this is AZTEC, and figure B, basically if you see, that is initially that was the AZTEC permanent data, but the new data is TP. And if you see figure C, that is the last permanent data was TP and the new is also TP. And in last case, that is figure number D, so last permanent data was TP and the new is AZTEC. Now let's see one example how we can reconstruct the data after doing compression using this CORTES algorithm. So if an AZTEC line is followed by the TP data, the length of the line is decremented and the distance between the shortened line and the first turning point is 1, as it is against 2 between turning points. So if a TP data is formed by a line, then the length between the TP data and the value of AZTEC line is 2 time units. Now there are some key points to note. Length of AZTEC lines are single units of time. Distance between the TP values is 2 time units. Transition from an AZTEC line to TP data, that is the length of AZTEC line is decremented. The distance between the end of the shortened AZTEC line and the TP data equals to 1. And from transition to AZTEC from TP data, the distance from the last TP data point and the beginning of AZTEC line equals to 2 time units. So let's see this example now. So the CORTES encoded data in this is 3, 10, 9, 5, star star 10, 12, 5, minus 10, minus 18, minus 5, star 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 30 and 10. So this reconstruct, now we have to reconstruct the ECG signal, and here if you see this 2 star, they mark separating AZTEC data from the TP data, and if you have 3 stars in series, that represent the mark separating TP from AZTEC, and the reconstructed waveform is as shown in figure. Now the next is the fan algorithm. This is another ECG data compression technique. It draws lines between the pairs of starting and ending points so that all intermediate samples are within some specified error tolerance, that is epsilon. So this figure illustrates the principle of fan algorithm. Starting by accepting the first sample as x naught, here small and capital X naught are the same. So they represent as the non-redundant permanent position, and it functions as the origin and also called the originating point. Then we have to take the second sample, that is x1, which is located at t1. Again, that is small or capital is in same in this. So we have to draw a straight line passing through x0 and x1 plus epsilon and designate it as line u1. As you can see here, this is u1 line. So we have to draw another straight line passing through x0 and x1 minus e or epsilon, and we have to designate this as L1. So you can see one is like x1 plus epsilon, other one is x1 minus epsilon. So we have two lines u1 and L1. So check if the third sample, that is x2, corresponding to time t2, you can see here x2 which corresponds to time t2 lies within the area bounded by the two sloping lines, that is u1 and L1. If it is so, we have to generate two new sloping lines, that is u2 and L2, that pass through now x0 x2 plus epsilon and x0 x2 minus epsilon respectively. Then we have to compare the two pairs of slope, that is u1 L1 and u2 L2 in this example, and we have to retain the most converging, that is restrictive slope lines. For example, in this is u2L1. Then we have to assign the value of x2 to x1 and read the next sample into x2. As a result, x2 always holds the most recent example and x1 holds the sample immediately preceding x2. So we have to repeat this process by comparing x2 to the next values of the most convergent slopes. And if it falls outside the area bounded by the two sloping lines, then the length of line joining x0 to updated x1 and its final amplitude is saved. So its final amplitude x1, which then becomes the new originating point x0, and the process begins anew. The sketch of the slopes drawn from the originating sample to future samples forms a set of radial lines similar to a fan. That's why this algorithm got its name as the fan algorithm. The signal is reconstructed by using the saved values which are connected by straight lines. This method guarantees that the error between the line that joins any two saved sample values and any redundant sample, that is actual sample value that was omitted, along the line is less than or at most equal to the magnitude of the preset tolerance epsilon. So this in this algorithm's reduction ratio mainly depends on the error tolerance. When compared to the turning point and AZTEC algorithm, the fan algorithm produces better signal fidelity for the same reduction ratio. This is the illustration and it shows the reconstruction of signal using the fan algorithm. So figure A shows the original waveform and figure B is the small tolerance and it will give reduction ratio of 5122201. Large tolerance is shown in figure C and it gives the reduction ratio of 5122115. And next is the smooth signal from C, that is we have taken L equal to 3 and we have used the smooth operation on that. So this figure is taken from book Tompkins by Tompkins on electrocardiography, biomedical signal processing. So this is all in this lecture. For most of the figures and topics, you can refer the book by DC Reddy, Biomedical Signal Analysis Principles and Techniques of Tata McGraw-Hill. So for now, thank you so much.